Let me start with this simple question. What happens when you pluck a string of a guitar? How do we end up hearing the same note or frequency regardless of where or how we pluck the string? If the string is fixed at both ends, then all waves in the string must have one characteristic in common. They must have zero amplitude at the ends. What controls this feature on a wave is exactly the frequency. The only allowed frequencies on a string are such that the respective wave shape vanishes at the ends. These have the name of harmonics or normal modes. So physics tells us that when you pluck a string of a guitar, you are in fact exciting a variety of normal modes with different amplitudes that add themselves in order to construct the form of the initial plucked string. The reason we only hear one of the frequencies, the first one, is because the form of the initial pluck resembles the most to the shape of the first normal mode, the fundamental mode, with the frequency of say 100 Hz. In reality, the other modes are there. The string is vibrating with a whole spectrum of normal frequencies at the same time. This is a closer representation of a plucked string, where you can see the second and third harmonics. Notice here how they have values of 200, 300, they are integer multiples of the fundamental mode. Most systems aren't this simple, and many of them don't even have any known explicit formula. One example is a black hole system. Last year, 2016, the LIGO collaboration unprecedentedly detected a gravitational wave signal produced by an inspiraling pair of black holes, their merging and the ring down of the resulting black hole, in complete agreement with Einstein's one-century-old predictions. In general relativity, gravity is a consequence of the deformation of space-time. The typical explanation follows these lines. Space-time can be represented by a sheet which becomes deformed as a massive body is put in place. If this was the Sun, the Earth would follow the curvature imposed by the Sun and rotate around it. If, however, you have two very massive bodies rotating around each other, then some of the energy involved is expelled in the form of ripples on space-time that propagate outwards. These are gravitational waves, propagating ripples on space-time. Simply put, gravity is the force that binds our bodies to the surface of the Earth. If a strong gravitational wave were to pass at your location, different parts of your body would momentaneously feel heavier or lighter than usual. The binary collision phase we'll be interested in is the ring-down phase, the stage where the resulting black hole vibrates with the excess energy from the collapse of these two very massive bodies. Vibration which gets translated into gravitational waves pretty much like the vibration of a string gets translated into sound waves. It also happens that independently on how you plug the black hole, for example by feeding it with a small asteroid, the resulting gravitational wave will have the same frequency, pretty much like the string. However, there is an important difference. A black hole system is open, in both sides. Waves go out to infinity or enter the horizon, the membrane from which nothing escapes, not even light. If you imagine a string going from the inside of a black hole to infinity, it is easy to see that if you pluck the string from somewhere in between, the ensuing wave will eventually dissipate into the black hole and to infinity. In fact, the actual shape of the gravitational wave signal is damped in time, like so. As the string, the wave is composed by many quasi-normal modes, mostly by the fundamental one. You see here that it must have 2 bits of information, which can actually be put into a complex number. The real part is the frequency of oscillation, and the imaginary part is the frequency associated with the damping. Despite all the knowledge we currently have on the quasi-normal spectrum of black holes, there is no actually explicit formula to compute them. It must be mostly done using numerical methods. Let's get to my dissertation thesis. The most important solved problem in physics is probably the formulation of a successful theory of quantum gravity. General relativity, despite working very well almost everywhere, is expected to fail in extremely energetic regions, such as near the event horizon, where quantum physics takes over. Something we'll be actually able to probe with gravitational wave astronomy in the near future. It is suggested that quantum effects near the horizon may generate some kind of solid structure just outside the black hole, which would block any exterior contact with the horizon, thereby closing the system on this side, pretty much like fixing the string just outside the horizon. The system is still open to infinity, having its respective set of quasi-normal frequencies, but how are these related with the ones from the pure black hole? Should they resemble one another? It turns out that they are completely different. My work here at Instituto Superior Técnico will be to investigate the evidence of the quantum barrier on the quasi-normal modes. This can provide a useful insight into the interpretation of the ring-down structure in future observations and to a better understanding of quasi-normal modes in open systems.